Welcome to the online version of Building with Ducts Inside Conditioned Space. My name is Bruce Sullivan. This training is made possible through funding from the United States Department of Energy and the Northwest Energy Efficiency Alliance. The training materials were produced by Earth Advantage. In an effort to encourage all new home builders in the Pacific Northwest to build with ducts inside conditioned spaces, Northwest Energy Efficiency Alliance has provided funding to create this training and additional resources to support builders, architects, designers, and subcontractors as they adopt this practice. The Northwest Energy Efficiency Alliance, or NEA, is an alliance of more than 140 utilities and energy efficiency organizations working on behalf of more than 13 million energy consumers. NEA is dedicated to accelerating both electric and gas energy efficiency, leveraging its regional partnerships to advance the adoption of energy-efficient products, services, and practices. Since 1997, NEA and its partners have saved enough energy to power more than 700,000 homes each year. As the second largest resource in the Northwest, energy efficiency can offset most of our new demand for energy, saving money and keeping the Northwest a healthy and vibrant place to live. As a market resource, BetterBuilt Northwest is committed to accelerating the adoption of the most energy-efficient building practices in residential new construction. BetterBuilt Northwest is a core component of the NEA Residential New Construction Program. And check out ductsinside.org for lots of additional information and resources. After completing this online training, you'll be able to describe the benefits of building homes with ducts inside. Identify which members of the design and construction team need to be involved. Evaluate 3 different design approaches to building ducts inside. Explain general principles and best practices for each approach. And access additional available resources to help builders, architects, designers, and subcontractors implement ducts inside. Ducts have a few problems. The main issue is wasted energy, and we'll talk about that at some length down the road. But right now let's talk about a few of the other issues that are related to ducts. One of them is indoor air quality. When the return ducts run through unheated spaces, they're often in dusty environments or places where there are all kinds of potential harmful materials, like fiberglass insulation, like dust, pesticides, and mold. Returns are under a negative pressure, so they suck air into the airstream whenever there's a leak, and so contaminants are drawn into the ducts from some unpleasant environments and could be distributed throughout the house. Also, you can have pressure issues that drive moisture-laden air into building cavities where water vapor can condense and support mold growth and even decay. Duct leakage can also create drafts and other uncomfortable problems. The first step with ducts inside is to decide, what's inside and what's outside. This is not always as clear-cut as it may seem. In most cases, the garage, attic, and crawl space are outside. Builders and tradespeople need to have a clear understanding of where the boundary is. We call this the thermal boundary. One important characteristic of the thermal boundary is continuity. If you were looking at a set of plans, you should be able to place a red marker on the plans and trace the thermal boundary around the entire building without lifting the marker from the paper. That means that the thermal boundary is continuous. We'll talk more about other characteristics of the thermal boundary a bit later. Even though we don't hang out in the ducts, it's important to recognize that ducts carry conditioned air, and therefore it's really an extension of the living space. A typical 2x6 wall has an insulating value of about R16 or R18, but ducts are only insulated R8. So what we're doing is extending the air in the living space through these ducts, and yet we're insulating it to only half the level that we would insulate the living space itself. Ducts also leak air, and if they're not sealed with mastic, the total heat loss from a ducted system is probably around 15 to 20%. So you're taking a 90% efficient furnace and you're turning it into perhaps an even 70% efficient furnace. Sealing and insulating the ducts reduces this loss by about half. But to get to the other half, you need to move the ducts inside. These pictures really drive home the idea that the attic is outside the thermal boundary. On the left, you see an infrared thermometer. It shows the temperature of the ceiling drywall at about 65 degrees. So that's essentially the building's interior temperature. The attic air shown on the right is only about 39 degrees Fahrenheit, which is very close to the outdoor temperature on this particular day. This demonstrates very clearly that the attic is actually outside the thermal boundary. Now, if you look at the surface temperature of the duct itself, it's about 50 degrees. That indicates that the duct is clearly warmer than the surrounding air, and you're really getting a lot of heat loss from the duct into the attic, even though the duct is insulated. This heat loss occurs in two different ways. First, you have conductive losses directly through the duct material itself. That's about half the heat loss. On the left, you can see an example of conductive losses. This particular yellow spot on the image on the left is actually a Y connection, a metal Y, and it's not insulated, so it gets a lot of heat loss. So it kind of exaggerates the effect a little bit, but you can certainly see the ducts standing out from the background on the infrared image on the left. Metal fittings that connect sections of flex duct can cause big problems. And on the right, you can see how air leakage affects heat loss. That's a distribution box with a lot of air leaking around through seams and little gaps that haven't been sealed. Let's look at one critical issue on the cooling side. This chart shows the daily temperature swings for 6 attics in August. There are only 2 days represented here. The smallest temperature swing is 50 degrees and the highest is 90 degrees. The temperature peaks out anywhere between 110 and 140 degrees. That's the temperature in the attic that these ducts are exposed to. And a similar thing happens in the winter when the attic air in the wintertime is pretty close to the same temperature as the backyard. Attics are hot in summer and they're cold in winter, and it's just not the place where you want to put ducts. In case there's any doubt that attic temperature affects the air inside ducts, this chart shows that high attic temperature corresponds perfectly with the high return air temperatures. These temperature measurements were taken in 3 locations: the attic, the return grill, essentially room air temperature, and the return air stream at the air handler. If you could zoom in on this graph, you would see that there's about a 10% increase in the air temperature at the air handler. That's the temperature or the heat that's being picked up as the air goes through the return duct in the attic on a hot day. And the same principle applies in winter, except that here in the Pacific Northwest, the ducts are losing heat to the cold attic, and this occurs for many more hours during the year than losses that you get during the cooling season. Here's work that translates this idea into operating efficiency. This study compares houses with ducts inside versus ducts outside, and you can see the fairly striking difference between them. The table at the top shows the total system efficiency, that's furnace plus ducts, for 10 houses with the ducts in a conventional configuration. If you averaged all those numbers, it's about 70%. That compares with houses with furnaces and ducts on the interior, which is between 97 and 99% system efficiency. There's really a big difference between the efficiency of the systems with ducts inside versus ducts outside. We know what happens to ducts over time when they're hidden in inaccessible areas of a house and they're difficult to access. The insulation deteriorates, leaks develop, pests such as insects, rodents, and other small mammals build nests in the ductwork. Repair workers or homeowners scuttle through the crawl space, and when they have difficulty getting through, they end up crushing the ducts or damaging them somehow. This is a particular problem with homes with very tight crawl spaces, and there are a lot of those out there. So many things can happen to ducts when they're out of sight and out of mind. Ducts also create pressure problems, and these pressure problems are much more severe when those ducts and the air handler are outside the conditioned space. Pressure imbalances can create air movement across the thermal boundary. That may pull nasty air from attics and crawl spaces into the living area. It may pull toxic gases from the garage into the living area. It may pull moisture-laden air into building cavities where it could lead to mold and structural decay. Here's how it works. If you have leaks in the supply side of the system, not all the air is getting back inside the house. You're going to starve the house for air, or at least those rooms, and it's going to create a negative pressure. If there are leaks on the return side, there's extra air pulled into the ducts from the outside. That's going to push more air into the house than there used to be, and that's going to create a positive pressure. These pressure problems could be minimal or even non-existent if the ducts were inside the thermal boundary. Benefits of building with ducts inside conditioned space. Ducts inside offer many benefits for builders. Energy use can be up to 20% lower. You can have smaller heating systems, smaller equipment, and smaller duct systems too. It's a good way to meet evolving energy codes. Both the energy codes and the voluntary certification and rating programs are going to recognize ducts inside as a significant energy savings. There may be higher tax incentives or utility incentives. There will very likely be less cost in building an HVAC system that's smaller and shorter and lower capacity. So if you're putting in smaller equipment and shorter ducts, there should be some cost savings there. Those savings may take a while to materialize in the marketplace as trades learn how to do these measures. In the Pacific Northwest, underfloor ducts are often installed in the cold and rain. Under these conditions, you're probably not going to do as good a job as you would if you were working inside in a fairly dry space. So there's this trade-off between doing underfloor installations in really harsh conditions and standing on a ladder to do the same work inside the building. It's also easier to do your quality control on that work inside the building than it is to inspect it if you're crawling through the mud under the house or you're up in the attic. You'll get better indoor air quality and better moisture management too. You'll also experience a competitive marketing advantage because especially the builders that adopt this practice early on are going to set themselves apart from other builders. It could be a really big marketing advantage as long as you capitalize on that advantage and don't just leave it up to the customers to somehow notice on their own. So there really has to be some kind of marketing push behind this. And finally, it just makes sense. Building with ducts inside conditioned space can be an important selling feature, but it doesn't sell itself, and so messaging for the consumer is extremely important if you're going to capitalize on the potential marketing benefits of adopting this new practice. Here are a few things that are really important to emphasize with consumers. Ducts move indoor air, and the ductwork is an extension of the living space. And so you don't want to put ducts outside the living space, you want them inside. Ducts inside makes homes more comfortable by maintaining better control over building air leakage and also by reducing the amount of heat loss and heat gain that those ducts are exposed to. You can improve indoor air quality by keeping the ducts away from those inhospitable places like attics and crawl spaces where they can potentially pick up some dust and dirt and pull it into the house. If ducts are out of sight, they're out of mind, and often invisible ducts can be damaged, and that damage can go undetected for a very long time. So putting the ducts inside the conditioned space really protects them from damage down the road. Modern efficient houses don't need as much heating and cooling, so locating the supply registers on the perimeter of the building, usually underneath the windows, is not really necessary. In an efficient house with a properly designed duct system, those registers are located in different places and usually not around the building perimeter. You can often use that as a visual selling point that this house is different. There's been more attention to detail. And finally, it saves a lot of money in heating and cooling costs. Here's a good way to help customers visualize the common sense of ducts inside. Running ducts through an attic or a crawl space is really not much different than running them through the backyard. Think about it this way. It really makes no sense for ducts to run outside because you wouldn't walk outside to go from one room to another, so why would your ducts run outside to go from one room to another? There are some potential challenges to building with ducts inside too. You can have design changes such as the issue of extra height in the building. You can have challenges finding space for the equipment inside the conditioned envelope. You may find that the trades are resistant to this whole idea and you have to overcome some pushback. Some people may view soffits as unattractive. Sometimes scheduling or sequencing of the trades can be an issue. You might lose some interior space, or you may have secondary impacts or ripples through the floor plan. There could be extra noise to deal with. There could be some cost complications. Sometimes bonus rooms are especially problematic and require special attention. The indoor furnace requires a condensate drain, and that needs to be anticipated. And finally, the location of the furnace can sometimes affect the location of the water heater because you want the same gas line to serve both devices. All of these challenges will be addressed as we move through the training program. Several of the leading builders in the Pacific Northwest are converting their operations and building with ducts inside conditioned space. Here are just a few of these major builders: Quadrant Homes, New Tradition Homes, Arbor Custom Homes, Legend Homes, and Habitat for Humanity. Let's hear from Vern Mallon again. This time he talks about Legend's experience with the ducts inside process and some tips for successful implementation. Here is a summary of the points that Vern made in the video so that you can review them later. Legend Homes started a best practices group so that they could research various building practices and improve their product. Ducts Inside came out of that process. They followed Energy Star details. They held team meetings with the HVAC contractor, the electricians, and plumbers to kind of avoid conflicts that might occur on the site. One of the things that the HVAC contractor did was to actually paint out the ductwork so that the plumber would be able to avoid the duct runs. The stair issue drove them to redevelop quite a few of their floor plans. 30 of the 84 plans that they use have now been converted. They were able to use coffered ceilings to run a lot of their ductwork, which gives some architectural interest to the various rooms. They required the HVAC installer to show all the seams of the ductwork in the plenums so that they could be sure that they were sealed properly with duct mastic. Overall, the house height increased by about 2 feet. Ducts Inside requires cooperation between a number of different players. In fact, most of the trades involved in the functional elements of a home need to work together. This includes the general contractor, of course the HVAC contractor, the framer, insulator, the folks that hang the drywall. The architects and designers, of course, are very important in the very early stages, plumber and the electrician. So all of these people have to communicate and work together. Specialization of jobs and responsibilities can lead to conflicts. It might be the plumber and the electrician, or the electrician and the HVAC installer. This is a common problem in new construction, but when we start to move ducts into the conditioned space, these problems can become a lot worse. Communication and cooperation are both essential for success. If you're going to do ducts inside, it simply won't work unless the general contractor facilitates communication and cooperation among the members of the project team. Later in this class, we'll dig into suggestions for ways that each member of the construction team can support a Ducts Inside project. This is a good time to mention a one-page document that lays out suggestions for each trade so that they know what's expected and who they might bump into on the job site. You can download a copy of this document from the Resources area, located at the bottom of this course page. It's also available for download on the ductsinside.org website. Let's look at several different strategies for applying Ducts Inside to your construction project. In general, you can think of moving the ducts into the conditioned space, or you can think of extending the conditioned space around the ducts. There are a wide variety of possible arrangements for ducts. We'd like to mention 6 that would find the broadest application in single-family residential projects. Right now, let's talk very briefly about these 6 strategies and outline some of the pros and cons of each. The 3 approaches that you see in the top row will be covered in more detail later in this presentation. So we'll dig deeper into dropped soffits, open web floor trusses, and conditioned attics. You'll find additional information on all these strategies on the ductsinside.org website. One of the simplest methods for ducts inside is the drop soffit. This is ideal for single-story buildings with a central hallway. It's a very popular approach with affordable housing developers who specialize in small single-story homes. Dropped soffits are not expensive, present few code issues, and they don't increase the volume of the conditioned space. In order to maintain an air leakage barrier, the top of the soffit must be enclosed with a rigid material such as drywall or OSB. You must decide what material to use and which trade will install it. We'll cover this in more detail later. Open web floor trusses are ideal for 2-story designs. The intermediate floor cavity allows access to every space on the lower and upper floors. In this approach, the furnace is most often located on the 2nd floor in a special closet or utility room. Because the height of the open web truss is generally greater than the 12-inch framing normally used, it may be necessary to adjust the stair risers on the inside and add siding on the exterior. A conditioned attic works well for many types of plans. It gives good access to all the areas of the house, and because there's ample clearance, there may be fewer conflicts between the trades. Conditioned attics must be carefully planned and executed for good moisture management and building code compliance. We'll cover these details later in the presentation. An inverted soffit is one way to enclose ducts that would otherwise be exposed in the attic. A rigid box that's usually made of structural sheathing is built around the duct. It's necessary to extend the air barrier from the gypsum board ceiling to the insulated box that covers the ductwork. This approach works well for a central trunk line, but it may become too tedious if the system has a large number of branch ducts. Keeping the branches as short as possible can help. This approach presents few obstacles, but it does require careful planning. Attic trusses are commonly used to capture additional living space under a steeply pitched roof. The same approach can be used to create a utility room that's fully insulated and sealed. This room can house the air handler as well as the return and supply plenums. It may also be used for major duct runs. One drawback to this strategy is that the side walls, sometimes called the knee walls, must be fully insulated and the backside covered with rigid material. Air barrier continuity must be maintained by blocking and sealing the bottom plate of the side walls to the ceiling gypsum board below. Also, this approach does increase the conditioned volume of the house. If a basement is part of the plan, this is a great place to locate the air handler and the ducts for the ground floor. The entire basement can be included in the conditioned space, or maybe just a section. Either way, the walls must be fully insulated and sealed. If you're building in a high radon zone, then additional precautions are necessary. Inverted soffit, attic truss, and conditioned basement are covered in full detail on the ductsinside.org website. Most houses will use a combination of approaches. This shows a rectangular trunk duct that will be enclosed in a soffit with laterals running between joists. Before we dig into a detailed description of the 3 ducts inside strategies, let's talk about the basic principles that apply to all of the strategies. It begins with design. Today, it's common practice to draw a square in the garage and label it FAU for forced air unit, and then the designer just leaves it up to the HVAC contractor to take it from there. Why would you omit such an important element as the HVAC system? You wouldn't leave the windows off of the plan. It's important to really think about where the mechanical equipment, including the ducts, are going to go inside the building. The first step is to choose the strategy that you plan to use. Is it going to be the dropped soffit, or the open web floor trusses, or something else? Or maybe it will be a combination of approaches. Then create mechanical drawings, not only in plan view but also in section, so that it's very clear exactly where the ducts are going to occur inside the house. In doing this, you'll want to consult the HVAC contractor because they're going to help you understand the size of the ducts that are needed and some of the limitations, perhaps on the way the ducts have to run, the fittings and the grills, etc. It's essential to involve the HVAC contractor early on because it's really important to have all of the information on the building plans. A lot of people are tempted to create a set of plans that are really just for plan review, but really don't go beyond that. And I understand why that happens because people don't want to raise any red flags with plan review, but with the Ducts Inside project, it will be very beneficial to have all of the information on the plans. For one thing, the plans are a contractual document that really ties all of the different trades together so that the complete plans have the final say on what will be in the building and how it will be done. If you leave the plans vague, it's not going to help in figuring out who's responsible for what parts of the project. The plans are also an essential communication tool because you use the plans to get bids and all the trades will know exactly what their scope of work is. If the HVAC contractor wants to know what his job is, he can refer to the plans. I think one of the reasons why plans have become less important is because, unfortunately, they don't always have the information that all the different trades really need in order to do their jobs. They're doing their jobs based on the conventional approach that they've always used. Since we're asking them to do something different, it's important to document those differences in the plans. In commercial construction, the plans hold a much more central place in the process because the buildings are larger and more complicated, but also because the information you need is right there. Complete plans are really essential, and we want to use them now not only as a contractual document, but also as that essential communication tool. Integrated design means that everyone is involved in the creation of the design. That means all of the trades guided by the general contractor. For the first Ducts Inside project, it's essential to have all the trades sit down face to face. If these people are sitting down together, they can agree exactly on where the components are going to be, how they're going to be installed, and what the construction sequence is going to be. The main thing is not to attempt business as usual. It just won't work with a project where you're trying to build with Ducts Inside conditioned space, at least not at first. As everyone gains experience with the new approach and they've established new working arrangements, it may be okay for the designer and the general contractor to exercise their knowledge without dragging everyone into a meeting for a new project. Take a look at the Project Team Guidelines for Ducts Inside Approaches document, which serves as a guide for general contractors and project managers. It's really important to know what's inside and what's outside the conditioned space. The thermal boundary separates the inside from the outside. Basically, the thermal boundary needs to have the same insulation value throughout the building, the same R value in all the walls, and all of the ceilings and all of the floors so that each component is going to have a certain insulation level. Sometimes the insulation is compromised by pipes and wires and even ductwork, and so you need to remember that no matter where you put these different mechanical elements, that the insulation still needs to meet the same minimum insulation level. If you're going to put insulation below a duct or above a duct, it has to have the same R value as the rest of that component. If it's a ceiling, we're talking about R38 and maybe even R50 or 60. If it's a wall, it'd be at least R21, etc. You also have to make sure that the air barrier is continuous, that there are no gaps or holes. Continuity is essential. The air barrier must be made of a rigid material, one that won't flap in the wind. The materials that are most often used are drywall, oriented strand board, plywood, and there are pressed paper products called thermoply and energy brace that are also rigid. Those materials will cover the insulation and also prevent wind from intruding into the insulation. The thermal boundary has two parts, the insulation and the air barrier. Those things need to be touching each other so the insulation is living in a six-sided box, where the insulation is touching all six sides of that box. And it's critically important on all the vertical applications such as walls. We haven't started talking about putting covers on insulation in attics and floors yet, and that may come down the road, but for now, any kind of vertical applications such as a wall or a knee wall or a skylight shaft or maybe behind a tub or a fireplace, all these vertical applications need to have an air barrier. The insulation needs to have this rigid covering, whether it's OSB or plywood or drywall or thermoply or whatever. Foil scrimcraft is a good way to locate these spots in the house. FSK is not an air barrier. However, it occurs in the same places that you would normally need to have an air barrier that it doesn't occur in conventional construction. FSK is a fire-rated covering that usually goes behind a fireplace. Sometimes it'll go behind a duct chase or underneath a stairway. Look for where the insulators would normally put FSK. Places where you traditionally see the FSK are the same places where you'll want to replace that FSK with some kind of rigid covering. Now in some cases, such as behind a fireplace, you'll often see OSB or plywood and then the FSK goes over that, but the point is that the rigid layer is in there. Air barrier requirements are explained very well in the certification program material, so if you're interested in more information about the thermal boundary, what the components need to be, and where those things need to be installed, check with your local energy rater or utility program representative. Now let's talk about where to put the furnace. A central location is always best. It's inside the thermal boundary, the duct runs are going to be much shorter, you'll encounter fewer obstacles, and it's possible to have a really short return or no return at all. If you want to eliminate the return duct, use what's called a direct return, where the air goes directly into the furnace through a louvered grill. There's no duct at all. It's not the choice that many builders make, but I just want to mention it as an option. The key with these spaces inside a house will be to make sure that you've got adequate clearance for general maintenance, filter changes, and that kind of thing. Be careful that you understand what the codes are and the local interpretation of those codes before you start squeezing all this equipment into a very tight space. Because floor area is expensive, you may be tempted to reduce the size of this mechanical space as much as possible, but you still need to make sure that it's not too small and everything will fit well. Don't forget that we're also talking about vertical space, not just horizontal. Especially if you're going to have filter racks and air conditioning coils, be sure there's enough height to accommodate those. The next challenge is going to be noise. There are quite a few things to think about when you minimize noise. As I mentioned, the furnace can be located away from noise-sensitive areas. It's probably not a good idea to put it next to a spot in the house where noise is going to be a problem. Say a bedroom, a child's nursery, an office space if absolute quiet is needed for working. Try to keep the furnace away from those kinds of noise-sensitive spaces. Also think about the equipment you're buying. A 90% efficient furnace is a lot quieter than an 80% efficient furnace. The higher efficiency, higher quality units are likely to be less noisy too. These higher quality furnaces may have better blowers, or variable speed blowers that are going to operate on lower speeds some of the time and therefore reduce the noise. Think about placing the unit on vibration pads. Think about sound insulation in the walls around the equipment. Put a solid core door on the room or closet that will help to dampen the noise. In extreme cases, you may think about high STC assemblies, such as drywall mounted to resilient channel or 2 layers of drywall. Also, correctly sizing the ducts will reduce duct noise. In some cases, making the ducts too small can cause them to whistle, especially through the grills. Use insulated flex to absorb some of the noise, especially right toward the end of the supply runs where it comes to the boot. It can be R4 because it's not outside the conditioned space, and technically no insulation is required to prevent heat loss, but the insulated flex is going to absorb more sound. And sometimes the R4 flex is really not more expensive than uninsulated flex. Locating the furnace inside the conditioned space presents several challenges. Let's look at these along with some potential solutions. The furnace will consume some floor area. Be sure to allow enough space to access filters, make repairs, and meet all code required clearances. Don't forget the height requirements or the extra vertical space for a cooling coil, a drain pan, and a filter rack. It's possible to run the return directly through a louvered door or through a very short section of duct that goes through the attic space. Even though we're talking about ducts inside, certification programs allow 5% of the length of the ductwork to run outside the conditioned space. That exception was created for just the condition that you see here, where the piece of flex duct goes through the attic. It's a very short run that gives you a little bit of extra sound deadening. You absolutely should use a sealed combustion furnace when located inside, and the combustion air needs to run to the outside. Don't forget to seal the faces of the top plates to the back of the drywall. This is usually accomplished by a strip of gasket material. Some form of seal is required by Energy Star and all the certification programs. High-efficiency furnaces have a drain line to carry condensate away from the combustion chamber and from the air conditioning coil. When the furnace is located inside the conditioned space, you have to protect yourself from possible problems with the condensate. Most people also want to see a second layer of protection with a drain pan underneath the air handler. This is probably the best way to go. Some builders use moisture sensors with an alarm that goes off whenever moisture is present in order to bring people's attention to the fact that there could be an overflow or a leak. Let's look at putting the furnace in the garage. For some of you, this may be the first step to take towards ducts inside. This makes sense if you want to make as few changes to your existing plans as possible. The furnace is already in the garage, why not just build a little insulated room around the furnace and take it from there? And I think this makes some sense. It can be a good transition to a better solution down the road when you can redesign the plans and include the furnace inside the building. So let's take a look at this one. This enclosed room in the garage really extends the thermal boundary around the furnace equipment and probably the water heater too. It needs to be fully insulated to all the same insulation levels that the house is insulated to. The tricky part is the insulation in the floor. It's possible to build up the floor insulation right on the concrete slab using rigid insulation. You need to get the same R value, so you'll need several inches of rigid foam, probably with some sleepers to support the subfloor and the furnace itself. Another way to accomplish this is to continue the floor framing from the house out over the slab so that you can fill that cavity with fiberglass or whatever insulation you're going to use, just as you would with the rest of the floor. Ceiling height may be an issue because you'll want to have enough space to get the supply ducts into the second-story floor. In this case, most of your ductwork is probably going to be in an open web floor truss between the stories of a two-story building. One of the things that you'll want to do is connect that furnace room thermally to the building itself. Leaving the wall between the furnace room and the house uninsulated is one way to accomplish this. Air leaks in the furnace cabinet and the attached ductwork could cause some naturally aspirated water heaters to spill flue gases into the space. So if you're using a naturally aspirated water heater with a B-vent, you'll definitely want to make sure that it's got adequate combustion air. Of course, the best solution is just to buy a sealed combustion water heater if you're going to locate it anywhere inside the conditioned space. The other possibility is to locate the water heater in a different space than the furnace. The furnace would be in an insulated room and the water heater would be outside. In the past, it was fairly common to cut a hole to the outside, maybe have a short duct running to the crawl space or running to the outside. That clearly defeats the purpose of building a tight, energy-efficient house and putting the ducts inside. Check with local code officials to be sure that your solution is going to pass muster. Ducts are not often designed in residential buildings. Instead, duct length and diameter are chosen by experience, intuition, and rule of thumb. It isn't necessarily a bad approach for conventional homes. Most heating contractors have learned over the years what size of ducts they need, and the system works pretty well. But now we really need to go back to the design step because we've changed the conditions quite a lot. Heating contractors need to develop new intuition about how houses are going to work now that the ducts are inside conditioned space. It makes sense to go back to this design step and do the full duct design to at least inform this new level of intuition. Many HVAC contractors get used to sizing systems for homes built to basic code, and often those systems look very much alike. With energy-efficient homes, especially with the ducts inside conditioned space, the thermal characteristics of the building will be much different. It's essential to perform an accurate calculation. This includes the insulation levels, window performance characteristics, and the building air leakage rate. And don't forget some of the basics, such as selecting the correct climate zone for the project. With proper inputs, the size of the heating and cooling system will be accurate, the system will function properly, and the occupants will be comfortable. Let's talk a little bit more about returns. The return is obviously needed to get air back to the air handler so it can circulate through the house. We want to keep that return as short as possible, and so locating the furnace inside the building really helps to minimize return duct length. But much of the noise also comes from air movement through that return. One solution is to have the direct return, as you can see in these pictures. The grills go right through the wall. The air handler is behind the grill, and there really is no return duct at all. A direct return is an option, but it does tend to be a noisy one, and many builders would not accept the look. Most people that have tried the ducts inside approach are using a very short section of flex. Many times it runs through the attic space. Because it's insulated flex, it absorbs some of the sound. This is really a good place to use that 5% exception that you have. That's the 5% of the duct length that is allowed to run outside the thermal boundary. Ducts in residential buildings are seldom designed. In a house with the ducts inside, the duct system should be smaller because of the lower building heat load. The warmer exterior surfaces from additional insulation and air sealing in the structure itself. Also, there's a smaller furnace, and shorter ducts create less static pressure, so there's less resistance in the duct system. Properly sized ducts also may fit better inside the conditioned envelope. If the system has AC installed or is AC ready, then you should size the ducts to the cooling load and not the heating load. Even though they're in the conditioned space, ducts still need to be sealed. We still want the air to get where it's supposed to go and not leak out somewhere along the way. It's not as catastrophic as it would have been in a conventional system, but it's still best for the air to go where it needs to go. Sealing ducts also reduces the potential for condensation in building cavities because the warm air is going to carry a lot of moisture with it. Air leaking from ducts could come into contact with some cold surfaces and cause condensation and the problems that come with it. Air quality can be improved because you're not blowing dust out from inside a pressurized building cavity. And finally, it just improves comfort if the system is working properly. The cool air is getting where it needs to be. The hot air is getting where it needs to be. Customers will be more happy and comfortable. Duct testing is generally also required, even though the ducts are inside, but it depends on exactly what rules you're following. Some of the utility programs will require a duct test unless the ducts are all visible at the final inspection. In most cases, the ducts are already covered by drywall at that point, and they can't be visually inspected, so a duct test is needed. When you do a duct test, you'll want to do a test that's called the leakage to outside test. It's a little more complicated than a total leakage test because it requires a blower door and a duct blaster. You're shooting for leakage of 1% of floor area. The standard for most programs is 6% of floor area. So you can see that you're really reducing the amount of leakage from the ducts dramatically. And the duct test will tell you whether you've achieved that 1% leakage target. It's not a standard of any kind, it's just a guideline for what you should probably expect in terms of leakage in an energy-efficient home with ducts inside. In an energy-efficient home, washing the walls with conditioned air isn't really necessary to compensate for the high rate of thermal transfer in a conventional home. In energy-efficient homes, the shell of the building is better insulated. It has fewer drafts and the windows are better. So this opens the possibility that you can locate supply registers on interior walls. You don't have to run the supply ducts all the way out to the perimeter of the building as in the past. The old approach of running your supplies out to the perimeter of the building was really a way to overcome a poorly insulated, poorly sealed building shell. The HVAC system was having to compensate for all that heat loss from the shell. Now that we've tightened up the shell, insulated it, and improved the windows, you can avoid the labor and expense. In addition, it's possible to deliver heated air at or near the ceiling. You don't have to deliver heated air from the floor because, again, you're not relying on the heat loss of the building to create convection currents and circulate air around the room. The tightness of the building is going to allow that heat to more easily fill the entire space. But there is one step that will ensure that this all works out. The key is going to be selecting the appropriate grill. The chart shows the difference in airflow from different types of terminal grills. The line on the bottom is the standard stamped metal grill that you probably find in most houses today. You can see there's quite a bit of difference. That simple stamped metal floor grill is probably not the best choice for good mixing in a room. Now, it's not to say that it can't work. You just have to think about this and make sure that you're going to get the proper throw and mixing of the air. The design guidelines for grills are included in ACA Manual T, which stands for terminal, and that procedure can help you pick the proper grill. Then you can go to the manufacturer's information and select the product that meets your needs. In some cases, these grills are going to be more expensive, but again, it makes some sense to put thought into this and select the proper grill for your application. These days, the heating and cooling calculations in all the ACA design manuals are done with software. Several commercial computer programs are available. Perhaps the most well-known is RightSoft. Now you can get similar computer power for free on the Better Built Northwest website. Here's a link to their design tool. The conventional approach in construction involves keeping the subtrades as far apart as possible. This approach of keeping a wide berth simply won't work in the Ducts Inside project. Communication and coordination are absolutely essential. In this section, we'll be looking at all the different people that are involved in the Ducts Inside project, exactly what they're supposed to do, and how they can work together. We start with the pre-design meeting. It should involve all the principal players in the project. Some utility programs offer a financial incentive to support these early design meetings. The meeting should involve the general contractor, all the trades, the designer, and possibly even the code official. And the purpose of this meeting is to get everyone on board. You want to locate the air handler and all of the ducts and registers. You want to think about duct design. You want to think about duct sizing. If you don't know exactly what sizes there are at this point, you want to be sure that it's on somebody's to-do list. You can go back and optimize those duct sizes and the spaces that they have to fit through later. You want to look at the framing details that are needed to accommodate those ducts. Where is the air barrier and what kind of material will be used to create the air barrier? What are the air sealing details? How will you seal the joints and gaps in the air barrier to be sure it's continuous? Finally, don't forget to identify any component of the building that could become an obstacle. These might include structural beams, junction boxes for ceiling fans, pipes, wires, recessed lights, and other things. Let's look at all the different players that need to be involved in the Ducts Inside planning process. It's logical to start with the designer, who is obviously going to have to attend the team meeting and be very involved in what comes out of that meeting. The first step is to commit to an overall Ducts Inside strategy. Will it be open web floor trusses, dropped soffits, a conditioned attic, or some combination of these? The designer needs to position the furnace or air handler in a central location, and then think about how that location will ripple through the floor plan. Does it affect lighting fixtures, pipes, and wiring? Where are the supply registers going to be located? Consult with the HVAC contractor in order to make sure that those decisions make sense. And also, what are the minimum duct sizes that need to be accommodated in the building cavities? The designer needs to take this to the level of literally locating every duct path from the furnace to the supply registers, and the designer also needs to represent that on the drawings in both plan and section view. And don't forget all those possible obstructions. For example, beams, ceiling light boxes, gas lines, and other potential places that might interfere with the duct runs. The general contractor is the quarterback of the team and needs to drive this process and keep everyone else on board. She needs to decide who will be at the pre-design meeting and then make sure that they actually attend. She needs to coordinate with the trades to minimize conflicts or arbitrate them if they occur. She needs to pick the best ducts inside approach based on her knowledge of the building techniques that are going to be required in that particular house. Any indoor location for equipment will be much tighter than a garage or basement. She needs to make sure that the equipment will fit in the designated space and will be accessible for maintenance. And finally, she needs to ensure that any minimum clearances and fire codes and all technical requirements are met. The HVAC contractor plays the key role in this whole process, so they absolutely need to be involved with the design up front and attend the team meeting before construction starts. The intuition and rules of thumb that HVAC contractors have developed working with typical construction simply don't apply to ducts inside. They need to revisit those assumptions by actually doing a full set of calculations on the building. Once they've gone through this process of calculating the heating and cooling needs of a particular house, or maybe several houses, or maybe a dozen houses, it's possible they'll develop a new intuition that is appropriate for this new approach. But in the meantime, they'll need to pay close attention to the actual thermal characteristics of the building when they do a manual J calculation. The exact insulation levels, the window U values and solar heat gains, and the window orientations are all key factors. Air leakage is one of those things that gets missed quite often because in most of the manual J software, you don't have an actual number for air leakage. It says something like very tight or very loose. In the past, a typical production home might have had an air leakage rate of 7 or 8 air changes per hour at 50 pascals. Today's production homes can have an air leakage rate of 3 ACH 50, and a high-performance home can be below 1 ACH 50. That's a huge difference that will have a significant effect on the design heat load and must be dialed in accurately. It's necessary to look below the surface of your software to understand exactly what those menu selections mean in order to properly characterize the building that you're working on right now. The HVAC contractor will also have to do the same thing with Manual D to design the ducts properly. Also, think about the opportunities to pull the supply registers back away from the perimeter of the building. Again, in these tight, well-insulated homes with fewer drafts, it's not necessary to push those registers all the way out to the perimeter in order to maintain comfort. So at least entertain the idea that you can avoid the extra material and labor that's required to get those registers all the way to the exterior walls. They'll use Manual T to select the proper terminal for the supply registers. The goal is to get proper mixing and really get good throw out into the room. And very often that's not going to be the typical stamped metal grill that we're accustomed to seeing in homes these days. It's going to be something a little more sophisticated, maybe something that might more often be seen in a commercial building. It doesn't always have to be a more expensive grill, but they should at least go through the process of figuring out which product is going to work properly. Now let's hear from Dave Salholm, production manager with Pyramid Heating, about his experience building with ducts inside. Consider marking the location of duct runs with paint so that all the trades know to keep their work clear. Think about ways to reduce noise either in the selection of the duct material or in the positioning of the equipment. Seal all the penetrations that you've made in the thermal boundary, so if you make a hole, you need to seal the hole. And finally, always use mastic paste to seal all the joints, including the gores and manufactured seams. It's important to emphasize that flex duct needs to be fully extended and straight in order to minimize resistance to airflow. In the field, there are many bad examples of flex duct that isn't installed very well and's created some real friction problems on the supply side of the system. Don't be afraid to cut the flex. The framer needs to attend the team meeting and pay particular attention to where the thermal boundary is. In many cases, framing is going to have to be in place to accommodate insulation and support the rigid air barrier material, and to identify all of the paths for the ducts and their enclosures. Some of the ducts inside strategies involve using drywall to create the air barrier around duct enclosures. It's up to the general contractor to decide whether the drywaller needs to be involved in the team meetings and exactly what they need to know and what they need to do. The drywaller's principal purpose will be to create the continuous air barrier of the thermal boundary. The insulator is really important in this process of putting ducts inside. Again, the thermal boundary is one of the key components of the whole strategy, and it's vitally important that it's done well. The insulator needs to be absolutely sure where the thermal boundary is and which sections of exterior wall might need rigid backing. They need to seal penetrations and ensure the full insulation value is installed around the soffits and chases. And finally, there may be a little bit of additional sound insulation that's required around the furnace room itself. It depends on the particular project whether the plumber needs to be involved in the team meeting. The plumber is going to need to know where to put the condensate drain for the furnace, and in some cases, when PEX pipe is installed near a heating duct, it must be insulated. So that may be something that's not often encountered in a conventional project. Be sure to coordinate the placement of plumbing runs, especially gas lines, with the HVAC contractor. The electrician is another trade that may not need to actually attend the team meeting. It depends on the project, and the general contractor can make this decision. The biggest potential interaction between the electrician and the ductwork will be the junction boxes for ceiling lights or other things like ceiling fans. It just makes sense to wait to run the wires until after the ducts are already in place. Don't forget this document that captures all the trade guidelines on one sheet. You can download a copy of this document from the resources area, located at the bottom of this page. It's also available for download on the ductsinside.org website. We've already taken a brief look at 6 different strategies for placing ducts inside conditioned space. Now let's dig into a detailed description for 3 of those strategies that are most common. For each one, I'll provide a description, mention some appropriate applications, and describe some keys to success. The strategies that we'll cover are dropped soffit, open web floor truss, and conditioned attic. I want to mention again that most projects will use a combination of approaches. There's really not one approach that's going to meet all the needs or overcome all the challenges. So in almost all cases, you'll basically end up using more than one approach. In this particular example, there's a rectangular trunk duct that will be enclosed in a soffit, and then the laterals come off of that trunk and run up inside the floor joists. So it's really a good combination of 2 different approaches. Let's start with dropped soffits. These are commonly used in residential construction to contain plumbing, place a cap on upper cabinets, or enclose light fixtures. And oh, by the way, you can use drop soffits for ducts too. It can be the most economical approach, and so it's often used by affordable housing developers. Soffits are framed below the thermal boundary, that is the true ceiling, to create a space to run the ducts. This approach is one of the few that brings ducts into what has traditionally been the conditioned space. It works well with ceiling heights that are about 9 or 10 feet. It also works well in single-story or 2-story homes, and it can be used for either a central trunk or for laterals. A typical application of a dropped soffit would occur in a central hallway where a trunk would run down the length of the hallway with very short branches serving each of the rooms along the way. The thermal boundary is above the soffit. The main issue with dropped soffits is who will install the lid of the soffit that serves as the air barrier. It could be the framer using OSB, or it could be the drywaller using gypsum board. If the drywaller is responsible, it would require a visit before the drywall typically goes up for the whole house, often called a pre-drywall visit. Most houses already get a pre-drywall visit for specific locations such as the wall behind the furnace. So if you're installing your furnace inside a closet or utility room that's really tight clearances, they'll probably come out to line that room with drywall ahead of the HVAC installation anyway, so they could do the soffits at the same time. Check with the code official about the fire blocking requirements for the soffit. Fire blocking in this case could be provided by solid wood blocking in the walls at the same level as the lower ceiling. Or you could line the entire soffit with drywall around the inside to create the proper fire rating for the cavity. As I said, the central hallway is a good place to locate a drop soffit. It gives easy access to most or sometimes all of the rooms. Supply registers can be located on the interior walls. Soffits may already be planned above the kitchen cabinets and can usually be added to bathrooms without being obtrusive. Or you can use the soffit as an architectural element. They can be used to create visual separation in large open spaces. Coffered ceilings create a space to run ducts around the entire perimeter of a room. It might be tempting to stick recessed lights in the soffit, so be sure that the recessed light doesn't interfere with the duct. Habitat for Humanity in Washington State uses this approach to keep their houses small and simple. They used a different approach. Drywall was hung on all the ceilings and walls, and then the ducts were installed. You can see where they've punched through the drywall on the left side of the photograph here to get into a different part of the house. The framing for the soffit occurred after all the ducts were installed and sealed. The lower ceiling in the hall creates an architectural feature, a kind of visual interest. When you walk down the hall into the great room, it opens up into the larger space with a higher ceiling. Locating registers on interior walls is a good idea to shorten the duct runs. To get good air mixing, be sure to consult the manual T grill selection. Here's another example from the same house. You can see that they drywalled the room first, installed the ductwork, sealed it, and then installed more framing to hold the soffits. This is another good example of working out the sequencing with drywallers, framers, and those that might be involved in pickup framing. Note that there aren't any lights in this soffit as you might expect to see. Instead, they used a surface-mounted light bar. Here are two more soffits. Can you see what's missing in these photographs? There's no air barrier above the soffit. In these cases, that's okay because there's heated space above and the insulation that you see is really just for sound. But it's a good illustration of how you need to think about installing an air barrier. If this were an insulated ceiling, you'd have to cap that soffit with some kind of air barrier material. You'd also need to seal the rim joist along the exterior wall. In this case, they've insulated that rim joist space and then covered it with an I-joist. Here are some advantages of dropped soffits. They tend to be lower cost than other ducts inside strategies. You don't really have many code issues except for perhaps some fire blocking. There's really no increase in the heating or cooling load because we haven't changed the shape or the size of the overall thermal envelope. It doesn't really increase the building height, and it can create some varied ceiling heights on the interior for some architectural interest. The disadvantages are that the soffits may run into structural obstacles such as stairways, sloped ceilings, or beams. The trades need to be scheduled a little bit differently, so you'll have to decide who is going to cap the soffit and what material they will use. The minimum plate height is probably around 9 feet. If you tried to do this in a house with 8-foot plates and drop the hallway down to 7 feet, it would probably be a little too tunnel-like. How do you make sure that you succeed with this strategy? The key is deciding who is going to build the soffit, who's going to line the soffit, what rigid material they're going to use, and when it should happen. If the soffit occurs on an exterior wall, next to a rim joist, you'll definitely need to seal that rim joist very carefully. It's useful to locate the supply registers on interior walls, and that way you can reduce a lot of duct length. If you do that, be sure to select grills with the proper throw and mixing characteristics. Be sure to size and design the smallest HVAC system that you can. And finally, don't forget to match the insulation levels around the soffit to the full R value in other parts of the building. Perhaps the most popular strategy for ducts inside is the use of open web floor trusses. Let's take a look. Open web floor trusses can be the most flexible ducts inside approach for two-story homes. With a centrally located furnace, ducts can easily run to any spot in the house. The biggest issue is truss depth. Most homes now use a 12-inch joist for a second-story framing. Depending on the duct design, the depth necessary may increase to 14 or even 16 inches. Proper duct design may allow smaller duct diameters, so this is a good example of where accurate system sizing and duct design could pay off, not only for reducing the duct size, but by reducing the depth of the floor trusses as well. On an existing plan, changing the floor framing depth could send ripples through the design. It can affect the amount of siding and other exterior materials that you have to install. If you're adapting an existing design, check the stair dimensions to be sure that a few extra inches can be accommodated with the current stair footprint. Many builders place the furnace on the second floor and use a downdraft furnace connected to supply ducts running through the floor trusses. The return runs a very short distance through the attic. This approach also works well with first-floor mechanical rooms and garages because an upflow furnace can feed a supply trunk that runs between the floor joists. Now let's look at another video where we go through a house that was built by Arbor Custom Homes and see how they've installed the open web floor trusses. Watch out for the sharp edges on truss plates. Pulling flex duct across a sharp edge could tear it. Trusses can be made with a rectangular duct chase built right in. It's relatively easy for the duct manufacturers to do this. This may be necessary if your duct diameter is rather large. You just have to specify where the duct chase will be and how big it is. It's a very inviting space to run all kinds of other things as well as ducts. So you have to be careful that other stuff like recessed lights, large diameter electrical wires, or gas pipes are not installed in this space. Be sure to coordinate with the other trades. The fire code may require that this floor cavity be compartmentalized into different sections, each one being no greater than about 100 square feet. So check with your fire code about how expansive this open plenum can be. Here's a good example of a conflict. Look to the right of the round trunk duct. There's a branch that goes around the recessed light. It does a 180-degree turn around that light. These old-style canned lights are not used much anymore. The LED fixtures installed in ceilings nowadays are much shallower. However, even the LEDs can complicate matters. A bit of slack in the electrical cable could save a lot of grief. One of the essential elements of this open web floor truss strategy is sealing the entire rim joist all the way around the building. That big open space is great for running ducts, but it also allows free air movement so that any leak in any part of the rim joist will flow through the entire floor system. Another issue is supply duct leaks that would pressurize the whole floor cavity and drive moisture-laden air out to the cold rim where it could condense and cause problems. So all of that rim has to be carefully sealed. It's not good enough to just shove a scrap of faced insulation up there in the rim area as we often see. It has to be fully insulated and then air sealed to prevent water vapor or air leakage from reaching that cold rim. The best ways to seal the rim would be to use vapor-impermeable spray foam and just coat the entire rim with a layer of 2 or 3 inches of spray foam and then fill the rest with some kind of fibrous insulation. Another method is to put the fiberglass insulation in first, cut a piece of rigid insulation or wooden blocking, fit it to the joist bay, and then caulk it in place all the way around so that there's no possibility for air to leak around that block. This is probably not on the scope of work for anyone in the construction team, so it's necessary to figure out who will seal this location and what the materials will be. The open web floor truss is used primarily in 2-story designs, and these often include a tuck-under garage with a living space above. That heated space above the garage can pose a special problem for this open web floor truss approach. First, blow-in insulation is required to properly fill the truss cavity without voids, so bats aren't acceptable here. Another issue is creating the support to hold the proper amount of insulation. Because the duct takes up most of the floor cavity, more framing has to be added below the duct to create additional space for insulation so that that insulation level there matches the insulation elsewhere in the floor. Here's a drawing that shows a little soffit below the duct to allow the same thickness of insulation to be installed below that duct as it is in the other parts of the floor. When ducts run through open web floor trusses over unconditioned spaces, they must be located as close to the subfloor and insulated with blow-in insulation. Another possibility would be to use a rectangular duct that leaves several inches of space for rigid insulation that would achieve essentially the same insulating value as the floor cavity. For example, if you used polyisocyanurate insulation, which is about R6.8 per inch, you'd need 5.5 inches to reach R38, which is the standard floor insulation level. So in a 14-inch truss, that would leave about 8 inches for a rectangular duct. If that duct is big enough for that branch, it would work out. You'd have to figure all this out with the HVAC contractor to make sure that you've got the right size duct in a rectangular shape and can get enough rigid insulation below that. Another approach for getting air into the living space above the garage is just to avoid the issue altogether, by not running the duct in the floor out to the perimeter. Instead, run the duct up into the wall that separates that living space from the main body of the building. In this drawing, you can see that that duct just runs up the wall and ends near the ceiling. Air shoots out into the room. The success of this is going to depend on how big the room is, but also how much throw you have in that register and what kind of grill you put on that register. You can also use I-joists in a similar way to the open web floor trusses. They can be ordered from the factory with holes already in the appropriate locations, or they can be drilled in the field as long as you have the proper hole size according to code. Here's a configuration that many builders are using. It's a downflow furnace on the second floor. The air is pushed down into a supply trunk in the floor cavity, and from that supply trunk you can attach all kinds of branch ducts to all parts of the building. In this situation, it's really a good idea to use that 5% of duct length exception allowance for a little bit of extra return that pops into the attic. It's a short loop and it muffles the sound. Seems to work out pretty well. Here you can see the base can from below. It attaches to that round trunk line. The base can is directly below the furnace up on the second floor. Placing the furnace on the second floor means there will be condensate from the condensing burner in the furnace and the air conditioning coil. Since the air handler is inside, it's a good idea to put a drain pan under it, but the base can gets in the way. Here's a clever idea that was developed by Bob's New Construction in the Puget Sound area. They've created a custom base can assembly that includes the drain pan. It's essentially wrapped around the base can. There is no possibility that condensate or leakage could drain into the supply ducts. Each of the 3 sections overlaps the section below it. Some builders choose to skip the drain pan and use a moisture alarm instead. The advantage of the open web floor truss strategy is that it's flexible. You can put duct runs and registers virtually anywhere on the first or second floors. It doesn't affect ceiling height. The disadvantages are that it can affect the overall height of the building and the amount of exterior surface material needed. It can also affect the stair configuration. You may need to add an additional riser. It does require careful communication between the trades because you're really putting a lot of stuff in that floor cavity. And don't forget the rim joists must be sealed. To succeed with this strategy, anticipate the design impacts such as stairways and other design elements that may be affected by a slightly deeper floor framing. Design the ducts to reduce the diameter and therefore the depth of the floor framing when possible. Decide how to address living spaces above unheated spaces. If you have this situation, really think through how you're going to accomplish that before you get started. Remember that any insulated open web floor truss has to use a blow-in insulation product to fully fill the cavity. Pay attention to those furnace room details on the second floor because it's bound to be a tight fit. Think through and specify the location of all the duct runs in the floor framing so that you can coordinate between the trades. Carefully plan the location of the furnace and the ducts, and don't forget to seal the rim joists. A conditioned attic involves moving the thermal boundary to the roof plane. It creates a large area of conditioned space above the typical ceiling. This also means that you have to heat and cool more building volume, which will increase the energy use slightly. However, savings from the increased HVAC efficiency should far outweigh the small amount of additional heat loss you get from that larger surface area and volume. This strategy works well for just about any home. The entire HVAC system can be placed in the attic of a single-story home, and for multi-story homes you can house the air handler and ducts for the top story. Be sure to carefully think through all the surfaces of the thermal boundary. If there's an attached garage, then you need a fully insulated and sealed wall between the conditioned attic and the unheated space above the garage. Here's a good example of a furnace located in an attic. The roof sheathing has been insulated with high-density spray foam. Spray foam is an easy way to insulate the lower surface of the roof deck. There are 2 general types of spray foam. Low-density spray foam has a density of 1/2 pound per cubic foot and an R value of about 3.5 to 4 per inch. Low-density spray foam, however, is vapor permeable, and so if it's left exposed, as you would see it in an unfinished attic, then that exposed insulation needs to be covered with a vapor retarder. In most cases, you're going to use vapor retarder paint. High-density spray foam is much more dense at about 2 pounds per cubic foot of finished foam. It also has a higher insulating value of around 6 per inch. While high-density spray foam is impermeable to water vapor and doesn't require a vapor retarder, it does need to have an improved covering with a proper flame spread rating. Again, this can be achieved with the proper paint. Most composition roofing products require a ventilated space below the roof deck. However, metal and tile roofing material are okay for this application. Spray foam is an easy way to create a conditioned attic, but is probably the most expensive. Another way to insulate the roof deck is to place rigid insulation on the exterior. The exact amount of rigid will depend on the overall insulation target for the roof. A good rule of thumb is that 40 to 60% of insulation value should be on the outside and the rest in the cavity. Climate zones may vary, of course. Expect 3 to 4 inches in most cases. Then fill the cavity between the rafters with fibrous insulation. Furring strips hold the insulation down and provide the required ventilation space. This strategy brings the entire attic into the conditioned space. For Oregon builders, the Oregon Residential Specialty Code requires that ducts be installed inside the conditioned space. But there's an exception in the code which allows them to be sealed and buried in a deep layer of attic insulation. In Washington, builders can earn code credits for these deeply buried ducts. No matter where you build, you might want to try this approach as you transition towards ducts inside. You could start the process by moving the air handler inside and then use the deeply buried ducts approach until you're ready to modify your standard designs to accommodate the ductwork to be fully within the conditioned envelope. Let's have a look at the Oregon Residential Specialty Code, or ORSC, requirements for deeply buried ducts. This aligns with the Washington State Energy Code Table 406.3 credit for deeply buried ducts as well. Essentially, the ductwork is installed so that it touches the attic floor. When it's not possible to contact the ceiling drywall directly, it can be as close as possible. This allows the ducts to cross ceiling joists or the bottom cords of roof trusses. Then the insulation contractor buries the ductwork in additional insulation. The ORSC requires that all of the duct connections must be sealed with mastic paste and flex duct be tensioned with panduit straps. As in the past, duct insulation is R8 and has a vapor barrier. These are best practices you'll want to follow no matter where you're building. To meet Oregon code, a minimum of R19 insulation must be placed over the top of the ducts. The insulation depth will vary depending on the R value of the specific material that you're installing. Here's an example. Typical blown fiberglass has an insulating value of R 2.7 per inch, so there would need to be 7 inches of fiberglass over the duct. Spray foam insulation can be used too. The thickness of the foam needed to reach R19 depends on the specific product being used. How can you and the building inspector verify that you have sufficient insulation depth? Here are 2 options. First, you could install insulation rulers or depth flags so the exact depth of the insulation can be seen at a glance. Second, you could place R19 fiberglass bats over the ducts and blow loose insulation to fill in around the sides. The key is that there's at least R19 insulation on the top and around the sides along the entire length of ductwork. Of course, when ducts run perpendicular to the joists or truss members, they will not touch the ceiling, so insulation will have to be piled up around the ducts even higher in order to get the right amount of material over the top. To comply with the ORSC, the air handler must be located within the conditioned envelope. Another way to insulate the roof plane is to use framing members to create a deep cavity for insulation. More builders these days are starting to use I-joists for roof framing. You can get them in a variety of depths anywhere from 14 to 16 inches and can pretty much get any depth that you want depending on how much space you need for insulation and for ventilation. The ventilation needs to go all the way from the eave to the peak of the roof. You can put a ridge vent at the top and then soffit vents for the lower portions of the roof. In the cavity itself, ventilation chutes should be attached to the bottom of the roof decking all the way from the bottom to the top. It's best to use some kind of high-density blow-in insulation instead of bats, because the flanges of the I-joist create little spaces that might allow little channels of air to start flowing through your insulation, and you don't want that. Another thing that's really important is not to penetrate your nice roof assembly with big holes like a large number of ceiling-mounted lights. In particular, avoid recessed lights. They allow a lot of water vapor to get through and also interfere with the insulation, so the spot right above the recessed light is going to get the double whammy. Warm, moist air leakage and a convenient cold surface. It's a great recipe for mold or decay. Another way to create a ventilated cavity in the roof plane is to use a parallel cord truss. Again, these vary in depth, so it could be from 12 to 16 inches depending on your insulation target. For ventilation, you would need a ridge vent, soffit vents, and the ventilation chutes. You'd want to use drywall on the lower cord of the truss in order to create your air barrier. It may be a bit tricky to connect the drywall on the lower cord of the truss with the wall below. A combination of solid blocking and air sealing foam will work for most situations. With parallel cord trusses, it's really essential that you use some kind of a blow-in insulation, either fiberglass or cellulose, because bats simply won't fill in around the web members of the truss. Here are some advantages of conditioned attics. They give you maximum flexibility. You can get to just about any place above the ceiling. It works with any kind of ceiling height. It really avoids most of the obstacles that you might run into in terms of beams and other structural members. There's less potential for conflicts among the trades or scheduling problems. There's no code issue. There's no increase in building height. It does create extra usable space. It can be an interior utility room for your furnace and ductwork. It could also be heated storage. But there are some disadvantages too. If you want to enjoy vaulted ceilings or high ceilings, you won't be able to use that space for ducts. There's a potential increase in heat loss. Again, it's probably not as much as you're saving from moving the ducts inside, but you are increasing the volume of the building. If you choose spray foam, consider this. It may be more expensive than other approaches. Plus, conventional spray foam has a very high global warming potential. There are relatively new options with low GWP, so check out HFO spray foams. Here are the keys to success for a conditioned attic. If you're using spray foam, be sure to consider the warranty of the roofing material. Compare the cost of low-density spray foam with a vapor retarder to that of high-density spray foam with a fire-rated covering, and choose the material that's going to be appropriate for your project. If you're using one of the framed options, be sure to carefully consider the air sealing detail where the roof framing meets the wall framing and to be sure that that can be sealed properly. Don't forget to plan how you're going to get the ducts across areas with vaulted ceilings or stairways. And if you do create a utility space in the attic, try to make sure that the ducts run in a logical pattern that keeps them out of the way of people moving through the space. Like everything else, the HVAC industry is developing advanced systems to meet the needs of the future. One huge change is the increasing energy efficiency of new homes. The design heat load of a 2,000 square foot house built to the Energy Star standard in the Pacific Northwest is about 28,000 BTUs per hour. Few manufacturers even make a furnace below 40,000 BTUs per hour, so you're automatically putting in an oversized furnace into that house. Not only that, but there's a strong push to reduce space conditioning loads even further. New initiatives such as Passive House and Net Zero Energy need far less, perhaps 10,000 BTUs per hour. And putting an oversized furnace in a house like that is like putting a V8 in a Vespa. If you're thinking that doing a ducted system correctly is just too much trouble, consider these new ideas. One manufacturer is addressing the need for smaller capacity furnaces that fit entirely inside conditioned space. These small furnaces fit easily in a small utility closet. The supply trunk is 6 inches in diameter and the branch ducts are only 3 inches in diameter, so the ducts can run inside with little or no special framing. One drawback is that this unit does not accommodate a cooling coil, so air conditioning, if needed, would have to be provided with separate equipment. Some of you may be thinking, wait, didn't they already try this in the 1980s and 90s? What happened to that idea? In those days, there were microducting systems that could move the same volume of air as a standard heating system, but do it with smaller ducts. This was accomplished by increasing the air velocity. This puts the ducts under higher pressure, which also increased duct leakage. A system operating under higher pressure also had to be designed differently. And sometimes high-velocity systems created too much air noise at the supply grills. What about the Detson furnace that I just showed you with the 3-inch ducts? Their compact furnace has a smaller heating capacity and therefore needs much lower airflow, sometimes not even as much as 400 CFM. The current thinking on microducting is a bit different, and it's intended to work with most standard air handlers. Instead of increasing air velocity and system pressure, these new microducting systems operate at medium to low static pressure and run as many 3-inch ducts to a space as needed to supply the heating or cooling load for that specific space. This can work well with almost any sized furnace or heat pump. This idea is terrific in homes with medium or small furnaces or short-run ducted mini-split heat pumps. This new microducting effort started around 5 or 6 years ago in partnership with the U.S. Department of Energy. The idea was to test this theory to see if the following could work. 1. Create a central manifold and then run multiple 3-inch ducts to each room. 2. Use as many off-the-shelf materials as possible. 3. Make it as simple as possible so that standard installers could easily be trained. This system is actually very similar to the PEX manifold water distribution system that we see in many homes today. A modern microducting system looks something like this. 2 to 4 3-inch ducts run to each bedroom. Each duct moves between 15 and 30 CFM of air. The 3-inch ducts allow the builder and the HVAC trades to run ducts in between standard joisted floors and up and down the walls, even 2x4 walls. It works well for lower load homes with good envelopes. Small, super high performance homes, such as those built to Passive House or Zero Energy standards, should consider a highly efficient heat recovery ventilation system. These two units use heat pumps to recover heat and have a small amount of space heating and cooling capacity. If the building loads are small enough and the climate is mild enough, one of these might be all you need. Like everything else, the HVAC industry is developing advanced systems to meet the needs of the future. One huge change is the increasing energy efficiency of new homes. The design heat load of a 2,000 square foot house built to the Energy Star standard in the Pacific Northwest is about 28,000 BTUs per hour. Few manufacturers even make a furnace below 40,000 BTUs per hour, so you're automatically putting in an oversized furnace into that house. Not only that, but there's a strong push to reduce space conditioning loads even further. New initiatives such as Passive House and Net Zero Energy need far less, perhaps 10,000 BTUs per hour. And putting an oversized furnace in a house like that is like putting a V8 in a Vespa. If you're thinking that doing a ducted system correctly is just too much trouble, consider these new ideas. One manufacturer is addressing the need for smaller capacity furnaces that fit entirely inside conditioned space. These small furnaces fit easily in a small utility closet. The supply trunk is 6 inches in diameter and the branch ducts are only 3 inches in diameter, so the ducts can run inside with little or no special framing. One drawback is that this unit does not accommodate a cooling coil, so air conditioning, if needed, would have to be provided with separate equipment. Small, super high-performance homes, such as those built to Passive House or Zero Energy standards, should consider a highly efficient heat recovery ventilation system. These two units use heat pumps to recover heat and have a small amount of space heating and cooling capacity. If the building loads are small enough and the climate is mild enough, one of these might be all you need. We've been talking about placing ductwork inside conditioned spaces, but here's another thought. The purpose of a heating and cooling system is to keep people comfortable. What if that could be accomplished without ducts at all? This is possible in high-performance homes with very low heating and cooling loads. Mini-split heat pumps and furnace-rated fireplaces are two ways to totally eliminate duct issues for small, efficient homes. For smaller homes with open floor plans, complete comfort can be delivered without a traditional central heating system. Because modern houses have much more efficient building envelopes, there really isn't a need to deliver heating or cooling to each room. One option is a fireplace designed to be a heating appliance and not a decorative element. Fireplaces that are approved for space heating will have an official Annual Fuel Utilization Efficiency, or AFUE rating. Another option is a mini-split heat pump. Units are available in a variety of capacities and can operate when the outdoor temperature dips below 0 Fahrenheit. These ductless methods will comfortably heat most homes up to about 2,000 square feet, maybe larger. Heat for small rooms will be adequate 90% of the time. For the other 10%, electric zonal heaters can be installed in bathrooms, bedrooms, and other remote spaces. For larger homes and those with more complex floor plans, a ducted mini-split might be a good choice. These mini air handlers are designed to fit in tight spaces and even be mounted in dropped soffits. They generally serve 3 or 4 rooms. If properly designed and implemented, the benefits of building with ducts inside far outweigh the initial investment of adjusting plans and getting members of your design and construction team on board. In the near future, we hope that ducts inside will become the new normal in residential design and construction because it just makes good sense. I encourage you to ask the other members of your design and construction team to view this training as a first step to bringing your ducts in from the cold, or the heat. To assist you through the adoption of ducts inside, BetterBuilt Northwest offers a website with more information. On the website, you'll also find CAD drawings for specific ducts inside strategies, and all the drawings that you've seen in this training program are available there too. Visit ductsinside.org. I hope you found this training useful. Please take a moment to complete the online evaluation form. Thank you for joining us.